Hello, everybody. Good afternoon. Welcome to the Theoretical and Computational Chemistry and its Applications session. Before to start, I have a communication because the second speaker of this session, Dr. Pantaleone, sent me an email where he said that he has connection issues. So I asked if the other speakers are agree to move him after to the end of this session of or the part 2. So I asked to Emilia, please, are you ready to do the presentation in the second, like a second person? Okay, because he has some problems. Okay, so welcome, Sergio. Sergio is arrived. Okay, we can start, and now I leave my place of chair to my colleague, Andrea Lombard. That I don't see, I think so, but okay, I can introduce myself, but it's a little strange. And I don't know, Andrea is not here.
I'm here.
Okay.
So I take over just for the first speaker, to introduce the first speaker, which is Noelia Faginas Lago, and which is going to present a paper entitled Carbon Capture and Separation from CO2 and 2H2O gaseous mixtures, a molecular dynamics study. Please.
Okay, share my screen. Share. Please, can you see my screen?
Yes.
Okay, so I talk about of the performance bilayer graph-3 membrane for CO2 capture and separation. It was evaluated using molecular dynamics simulations. Gas absorption by porous material has been investigated as a phenomenon to ground technologies aimed at reducing greenhouse gas emissions. Among the greenhouse gases, CO2 is the most abundant and is regularly released into the atmosphere. So we need to develop the technologies to understand how storage this gas. How you know? The graphene is a class of carbon-based materials and formed by a single atom thin planar membrane with remarkable properties for gas absorption and separation. Nanoporous graphene is reported in literature as a promising porous membrane material. However, it tends to form aggregates that limits its gas uptake capacity. So it's necessary to find an alternative to the porous graphene. An alternative is the alpha graphenes because are single atomic layers arranged as a function of the carbon-carbon triple bonds bridging two adjacent hexagons. For our system in study, we have chosen the graphene 3. So, for modeling the intermolecular interactions, the total potential energy of our system is split into electrostatic and non-electrostatic contribution. The electrostatic contribution is calculated using a standard Coulombic summation by assigning point charges that is given by Q in this figure, showed in this figure, point charges to the interacting molecules, where the di and quadrupole moments of molecules were considered. Meanwhile, for the non-electrostatic contribution, is expressed using the improved Lennard-Jones potential. The formulation of the improved Lennard-Jones potential is given by this formula and requires 4 parameters. In particular, note that the parameter beta is a parameter that does not compare in the classical Lennard-Jones potential, and it corrects the dependence of the interactions of the internuclear distance, improving the potential function at the asymptotic region. So the molecular dynamic simulations were performed in a simulation box with the dimension 72 times 62 times 280 times. The CO2 and 2 water gaseous mixtures with equal fractions of CO2 and 2 and water molecules was generated randomly, distributing the molecules, how you can see, inside the simulation box. For the membranes, the graphene structure were optimized by means density functional theory. Here is given the reference. In order to mimic the post-combustion condition, we consider 4 different temperatures in our simulations. 7 different amount of gas molecules had been loaded into the box for the simulations to investigate the influence of the pressure. The amount of initial gas was computed according to the Pegg-Robinson equation of state. All molecular dynamic simulations were performed by using the poly package during 5.5 nanoseconds. We have used the improved Lennard-Jones for the non-electrostatic interactions, and the cutoff distance for improved Lennard-Jones and electrostatic interaction were set up at 15 angstroms. So here I show the first results. In the left figure shows the permeation events as a function of time. It can be seen that CO2, the violet line, has a higher permeation rate than water and N2. The results can be verified by looking at the radial distribution function profile that is given in the right part of this figure. We can observe that the CO2, always violet line, has the largest and highest peaks, meaning that the CO2 is more likely to be located near the carbon atoms of a layer. So, in this slide, I would like to show you the results of permeance as a function of the pressure and temperatures. The left figure shows that N2 pink line are slightly affected by the pressure. On the other hand, CO2 and water, blue and orange lines respectively, tend to decrease with the increase with the pressure and temperature. So we can say that CO2 still has the highest gas permeance. Here I show the unit of gas permeance. Furthermore, we calculate the permeance selectivities as a function of the temperature. We can observe that the CO2 and 2, black line, and water and N2 green line. The black line overlap with the green line, having similar values ranging from almost 5 to 6.5 selectivities. On the other hand, the blue line water CO2 selectivity is around 1, which implies that the bilayer membrane is not selective for CO2 water separation. In this slide, I show the zeta density, that is a plot of the mean number of density of gas, different gases along the zeta axis, where zeta axis is perpendicular with the layer. Here is the displaced the layer. The highest peaks of CO2, the violet line, indicated that layers exhibits a strong absorption of CO2, especially inside the interlayer region. Also observed sharp peaks outside the layer at a distance around 3.4 angstroms from the surface for all gases. Okay, integrating the zeta density and plot it versus the initial pressure, we obtain the curves and the gas uptake as a function of the pressure. Observe that the gas uptake is linearly proportional to the initial pressure. The figure shows that the CO2, in this case red line, has the highest gas uptakes and absorption coefficients. This coefficient decreases as the increasing of the temperatures, that is shown in the right side. If we estimate the slope of the absorption coefficient, we have obtained the total absorption selectivities using these formulations, and is given in this table. This table shows that B-layer exhibits a high CO2 and N2 total absorption selectivity at low pressure and temperature. So we can conclude that molecular dynamics can determine properties like gas uptake, permeance, and selectivity. The bilayer membrane has high CO2 and water permeance compared with N2. Also, the interlayer absorption selectivity of CO2 and N2 and CO2 water are about 20 and 2 respectively. So that implies that the layers are not selective enough for CO2 water capture and separation. With this, I finish, and I would like to thank us for the attention, and I would like to leave in background a simulation, a movie of the simulation of the molecular dynamics of this study. Thanks for the attention.
Okay, thank you, Noelia. And now there is time for at least a quick question from the audience. So, questions? Okay, if there are no questions, now I think that Noelia can start again to be the chairman of this session, and I'm going back to be a simple participant. Thank you.
Okay, thank you, Andrea. And sorry, I stopped sharing. Okay, so I would like to present the next speaker is Emilia De Aragao from Master Up, is a PhD student, and she will speak about the gas absorption of graphene membrane. So from a computational point of view, she will explain about the impact of the introduction of the induction interaction term in the potential interaction. Please, Emilia.
Oh, can you see?
Yes.
Wait a minute. Okay. Can you see? It's fine.
Yes, you can start.
Okay, thank you very much. So good afternoon. My name is Emilia De Aragao, and today I will present my work, the contribution for this workshop. My work is called Gas Adsorption on Graphene Membrane, Impact of the Induction Interaction Term on the Computational Cost. Here is the structure of my presentation. I start with the introduction. I'll talk a little bit about the methods, the results, and the conclusions. So for context, we now know that it has been, in the last few decades, rising the global emission of carbon dioxide, which has for impact the phenomena that we call in general climate change and the rise of global temperatures. So the impact, the carbon dioxide emissions are caused in general by manufacture of materials and generation of power, and as it has a very important impact in climate change phenomena, it is very important to investigate a new material that can be used to capture this gas in the flue gas of the usines. So examples of materials are metal organic frameworks, dolitic imidazole frameworks, and carbon-based membranes. So, for instance, here I have some examples of membranes. But while we have a very large list of candidates, we really need to emphasize that we have to see if the economic cost and the selectivity of the material capturing the CO2 is high, and the economic cost is not so high, so it won't impact so much in the price of those. So it's very important that we study these materials before trying to apply them, and to do so we can use molecular dynamics simulations. And in our group, we are interested, as we have seen in the presentation before, we are interested in the graphene membrane. That is this membrane that is constituted of benzene rings held together by a chain of carbons in triple bonds. And we wanted to try and see how is the selectivity of this membrane in relation to carbon dioxide. But knowing that in the flue gas we don't have only carbon dioxide but a mixture of other gases, we have also to take into account if this membrane also captures water or nitrogen, and how effective is the capture of carbon dioxide. And in order to well describe the interaction of these molecules with the membrane, we have to use we have to improve the code. We have to well describe the forces that are at play in our system. And for that, we are using an open source code called DLPoly that has a very particular thing that since it's an open source code, the person who is doing the work can write and contribute to the code, and so we can implement a new expressions of potentials. And as we saw before, in the group we are working with improved Lennard-Jones potential. I won't come back to this equation since it has been explained, but we are also interested in describing the induction interaction between the gas molecules. The induction interactions involves the water molecule with the carbon atoms of carbon dioxide, the oxygen atoms of carbon dioxide, and the nitrogen atoms. And we have tried to implement this in the code of DLPoly and do some simulations. But the problem is that when we take into account this induction potential, we have a computational time that is 5 times larger than when we take into account only the improved Lennard-Jones potential. And that is a problem because here in the simulations I did, I am using a very short time. I'm only doing 600 steps with femtoseconds, so it's a simulation that only lasts for some seconds, less than a minute. But in order to really estimate the energy values, we have to have a longer simulation times. And we cannot have longer simulation times for this, for taking into account the induction, if we have such a time difference. If, for instance, I take 2 days to calculate a system with just the improved Lennard-Jones potential, I'll take more than 10 days to calculate the improved Lennard-Jones potential. So what have I tried to see in the code? What can I could change in the code that could help improve this computational time? So I've tried first seeing if the impact was in the fact that I'm doing simulations with just the CO2 or the gas mixture. And I saw that the impact on the time is around the same. It's 5 times for each case. Here is longer than there because I'm taking into account more molecules. So it's natural. But then I decided to see the computational time of each steps in the forces routine. And I saw that for the eval sum, it's taking 4 times longer to do all the loops. This is for one time step, just one cycle. So it's already taking 4 times longer than when I use, in comparison, when I use improved Lennard-Jones potential. And so I also try to see if the implementation of the induction subroutine has any impact. And I see that now I have a time that is around 5 times longer than this one. So here I have an increase of 4. I have a times 4 times longer, and here I have 5. And in the end, I have a time 5 times longer. So what I have to improve in my code is the way that this subroutine is written. And for now, I have not seen a way to improve, but it's a project for the future. What I could do was to see how to improve the description of this subroutine. What I observed is that for the induction subroutine, we had that the induction potential only involves the molecules in the gas phase. But in my code, I am taking into account the induction. I am calling the subroutine even when I am taking into account the atoms of the graphene membrane. And this is a useless increase of time because I don't get any energy results off of this because it's a potential that only involves the gas phase molecules. So I've implemented a conditional at the call of the subroutine to only call the subroutine when it's when I am dealing with the carbon or the oxygen or the nitrogen of the gas molecules. And what I have seen is that it works. I don't have the increase I was observing before. And in the end, I only have a time that is 4 times longer than when I'm using the improved Lennard-Jones potential. So this is what I could do for now, improvements of my codes. And what I think to do in the future is to improve the eval sum subroutine in the case of the calculations with induction potential and the improved Lennard-Jones potential. But it's something we will see the impact, And in the future, we will do calculations that take longer time, and we compare what is the impact on the energy and the description of the system. So I thank the European Union for funding my project, and I thank you for your attention.
Thank you, Emilia, for the nice presentation. Now is the time for some questions, please. Is not a some question? Okay, thanks, Emilia. Fine, thank you very much. And we can move to the last speaker that I have not clear if it's Federico Sabatini or Sergio Tasso.
It's me.
Yes, because I
okay. No. I have not clear because in the presentation compare all names like presenters, and so okay, Federico Sabatini and Sergio Tasso from the University of Perugia with the talk entitled Improvements to the GLOREP Federation of Learning Object Repositories. Please, can you start? Okay.
Okay, can you see the slide?
Yes, of course.
Okay. I'm starting. GLOREP is a federation of distributed repositories aimed at facilitating the sharing of chemistry learning objects. GLOREP uses a hybrid network structure where each website has a home database with learning objects, and these learning objects are shared among the federates using a synchronization method. These learning objects are stored following the standards of IEEE LOM, and their metadata are shared to the federation using the central node. This central node hosts a shared database, and each federate works like an intermediary between a user subscribed on his website and the real federate where the full learning object is stored. In this way, a user signed up on a federate can access to the full learning object existent on the federation, and in this way, the user doesn't need to subscribe on each website. One of the main features of GLOREP is the automatic cataloging of learning objects. The old GLOREP was based on Drupal 7. Many plugins are written and installed on this old version to allow to operate, which include synchronization and cataloging, searching, etc. The synchronization was managed performing remote queries over the database, the shared database, and the installation was manual and a bit tricky. This is a figure showing the old GLOREP structure, hybrid structure. In this old GLOREP, each federate has direct access to the shared database. This permits to guarantee the normal operation of the federation if a node goes down. For example, if the central node goes down, a federate can still offer all the old learning objects of other federates and owned by itself. But if the central node goes down, the synchronization stops until it goes up again, and in this way, it can offer the new learning object created. The improvements to the new GLOREP consist in a migration from Drupal to Laravel. Laravel is a framework written in PHP. This implementation permits to create a new synchronization architecture based on RESTful API. New features are added too, and the installation now is more and more easy because it's done using a Docker Compose method. This figure shows the new hybrid network through the shared database is accessed through this glorep API, and the advantages of old glorep are still here. The synchronization between local database and a federate and the central node of the federation is done using this approach on the API. We are two variables, last sync and last TD. The local federate sends metadata of learning object having a timestamp greater than last synchronization value. Then, if the central node return success or error, if success means last synchronization at success, and last sync value is updated. Then the federate asks to the central node a new list of learning objects having ID, a shared ID greater than last ID I stored. In this way, the central node returns this list to the federate, and the federate can store this new list. What's Laravel? Laravel is a powerful PHP framework using the MVC design pattern. With this design pattern, a user visits a root. The root loads the controller. The controller, using models, can read and write to the database. Then the view is returned to the user. New feature in glorep, thanking to Laravel, has been possible to be written using a new graphic. In this figure, we can see the new feature consists of automatic cataloging of keywords of learning object. Not only the category, but now we can automatic cataloging the keywords too. In this figure is showed the new nice graphic of cataloging of categories. In summary, improvements to the glorep consist of improvements to the search engine, the possibility to add the new areas other than chemistry to the platform like mathematics and computer science, a new system to manage the users, a easy installation and update system, the possibility of create on join to a federation, a more secure environment, and the possibility of making the site multilingual. In conclusion, glorep has been redesigned from Drupal to Laravel, which permits to have improvements to the security, new features, a more efficient synchronization mechanism, and also two new areas such as mathematics and computer science, other than the old chemistry. I'm done.
Thank you very much for this nice presentation. Now, thank you, Federico. Now it's time to discuss this paper. Some question. I have some curiosity about the cataloging. Have you used the standard numbers, so like in the bibliothèque, the standard numbers to cataloging the topics inside the glorep?
Yes, we used the standard number. Each subject, like chemistry, mathematical, sciences, ID, and
are a world or are a European? These numbers.
Excuse me.
These type of numbers are the standard for all world, or only depends of the countries of the continents?
No, are the standard for all the world.
Oh, perfect. Okay, perfect. Some more questions?
I have a question for Federico. The difference among Laravel and the old CMS, also in terms of weight in the system, etc. Did you find also advantages, or
there are
also some counter? Some difficulties.
Only the pro using this framework, because Drupal has more feature than what glorep need. So I see last about 10 update of Drupal was a security issue about a feature that glorep doesn't use. For exception is jQuery, but update jQuery is really easy. And so glorep 7 using Drupal 7 has many vulnerabilities causing from this using of feature of Drupal, which I don't need. So using Laravel, we have only what we need.
Okay, thank you.
If there is no more questions, thanks all the speakers of this session, the part one of this session. I think so. Stefano Pantaleone is not arrived. We wait for him for the second part of the session, and we will see in the same room at 5:30. Okay, enjoy the coffee break. Bye bye.
Bye, thank you.
Noelia? Noelia?
Dimmi.
Pensavo di farlo comunque il cambio sul programma, così avete il chairman alternato. Io mi sono dimenticato, scusa.
Vabbè, non lo fai.
Non ti preoccupare.
Lo faccio adesso, dai, così almeno siete scalati.
Ma io l'ho fatto, ma non ti preoccupare, Osvaldo.
No, ma adesso lo posso fare
Osvaldo, va
tranquillamente.
bene, sì, ok, grazie.
Ciao.
Ciao. Sono andata a cercarti, ma non c'eri tanto per cambiare. Cioè, vabbè, sei pronto?
Questo è ricomparso.
Che no. Allora lo chiami, io adesso ti introduco, lo chiami e
Io mi introduco alla sessione.
tu introduci la sessione, dopo ti introduco io a te. Dice Ugo che il massaggio è stata una cosa ottima, che merita la pena. Allora la settimana prossima. Sì, Ugo stava tornando, dice che ha una paura di prendere col motorino dell'acqua perché è andato dalla sorella, ha dovuto andare al lavoro perché come sta come caposezione deve andare a fare delle puntatine. Dopo ieri è andato a chiedere a Enfanzu di che nazionalità era. Enfanzu è il cameriere del Moderno, perché hanno bisogno di un interprete che parla una lingua mai sentita africana e non lo trovano a Perugia. Lui ha detto che è da Gambia e che ha detto che conosce quella lingua ma è molto stretta, che dovrebbe sentire, ha detto, cioè, ha detto è come se tu un spagnolo che ha viaggiato le chiedi se conosce qualcosa di italiano, ha detto ma devo sentire se lo capisco.
Possiamo iniziare, direi. Okay, it's time to start the second part of the session, of the workshop. And I'd like to ask the previous speakers, the speaker of the previous part, Stefano Pantaleone, if he's connected. Okay, I think he's not online. Okay, if so, I have to. I'm not supposed to be the next speaker, so I pass the control of the chairing of the session to Noelia for the time being.
Okay. Hello, everyone. Again, I introduce Dr. Lombardi from Dipartimento de Química, Biologia e Biotecnologia, University of Perugia. He speaks about classification of shapes and deformations of large systems by invariant coordinates. Please, Andrea.
Okay, let me try to share the screen, of course, in the meantime. Need some time, sorry.
If you prefer, Andrea, can I share if you want?
Wait, because there is something. It's frozen, and I don't know why. Okay, I try to disconnect. Okay, let me check now. Okay. Can you see the screen?
Yes.
Okay, let me put.
Can you start, please?
Okay. Okay, if you can see the screen, I start my presentation here, which is about the classification of shapes and the formation of large molecular systems, particularly biological molecules like proteins. As you know, proteins experience a very tight connection between the global 3D structure and their biological function. And we know that even small differences in the complex structure of such molecules can destroy completely the biofunction of the molecule. And it is very important, it is a key point for the theoretical and computational study of biological molecules such as protein to have some methods, a systematic approach to the classification of the structures, and in order to be able to distinguish differences between these structures and to catch the essential properties which really matter for the biological functions. Which is the approach that I want to propose here? It is an approach based on invariant coordinates that can be obtained in our case by starting from hyperspherical coordinates, which can be defined for any kind of molecular system made up by an M particle, and can be even very, very big number, like in the case of proteins. And we can, using Cartesian coordinates that can be properly scaled according to the atomic masses, we can build up a matrix, a Z matrix, a coordinate matrix, just disposing on the columns the scaled vectors. Then we can consider the action of two kinds of rotation on this matrix, and particularly we have to consider the rotation in space, ordinary rotations, which didn't change, didn't modify the structure because the global structure of the molecule is invariant, of course, as you know, with respect to ordinary rotation. And also we consider the kinematic rotations, which are, from an abstract point of view, are actually rotations, but they act just altering and modifying the relative positions of the particles in a certain way. The point is that in such applying this kind of rotations, we can ask ourselves which are the properties of this coordinate matrix that remains invariant with respect to this kind of rotations. And we can do that applying a matrix decomposition, singular by decomposition, to the matrix Z, and in such a way that we naturally split this matrix into three matrices. We can recognize the R and K matrix that we use to perform ordinary kinematic rotations, plus a third matrix, which is very, very funny, in particular because it is filled up by zeros, with the possible exception of these diagonal entries, which are identified by denoted as xi's, and which are invariant with respect to this kind of rotations and are subjected to this kind of inequalities. By the way, the xi's are related to the principal moments of inertia by this relationship that you can see here, and we can assign to those quantities the physical meaning of giving us an idea of how globally the masses are distributed with respect to the body frame and particularly to the principal moment of inertia frame of the system. But let me get straight to the point. We can give an expression of those quantities by spherical coordinates, and by this operation we can put into correspondence in a unique way the size, the range of the size with one of those of these triangles, spherical triangles. And in particular, if we select the case n equal 4, which means 4 atoms or 4 centers in general, we can observe that as due to symmetry reasons, the space of the size can be projected into a double triangle. Each half of this triangle corresponds to the chirality sign of the system. I mean, the two possible enantiomeric versions of the system. What we can do, let me go straight to the point. We can use these quantities to build up deformation indexes, for example, in this way. This is just one of the possible uses of these size quantities. And these deformation indexes can measure the distance of the structure, of the global structure, from the spherical, the perfectly spherical structure, in such a way that they account for deformations globally. And how can we apply these indexes and these psi coordinates to real systems? Let me show some possible use. For example, we can, concerning protein structures, we can start figuring out how those indexes can be applied to single amino acids and then to amino acid chains. We can, first of all, notice that each amino acid can be sketched as a 4-center system. I mean a tetrahedron in this way. This means that we can calculate for each amino acid the triple of the size, and then we can map on this triangle, on the space of the size, the corresponding value. For example, to understand what I want to propose to you, you can think to the very famous Ramachandran plots. In this kind of plot, which are applied to used in proteins, essentially, Ramachandran had the idea of plotting in a space the values, all the possible values of the angles psi and phi of the protein backbone, obtaining this kind of representation, which determine where are the allowed subspace for real native structural proteins. We can try to do the same with our indexes, but in a better way, because we have actually one more parameter indeed, and also we have the possibility of distinguish between chirality sign, which is an essential in this case for proteins, because we know that there is the same chirality signs in amino acids in proteins, but we can measure the quantity, the distance from the how much chiral it is, in a sense, a single amino acid in a single protein structure, and so on. Then we can make statistics. This is an example. For example, we can plot in this two-parameter space the values of the Psi1 and Psi2 obtained examining tens of thousands of protein structures from the protein data bank. And this is a possible use. You know, there are a few outliers here, as you can see. And another possible use is to try to build up a footprint of the amino acids when they are present in the protein structure. For example, we can start with the 4 different protein structures, and then we can plot the glycine footprint, I mean the plot of all the deformation indexes obtained examining each glycine in each of the 4 different proteins. And we obtain this peculiar shape, as you can see, which is, in my idea, the footprint of the glycine in these proteins. The same can be done in principle for any amino acid, for example, proline. Here, and you obtain a different footprint. These are only 4 proteins. We can ask ourselves if this is true for all the proteins, and what makes this footprint really meaningful in this kind of representation. And the answer is yes, because I try to analyze tens of thousands of protein structures from the PDB, protein data bank. I consider proline again and glycine, and you can see that the previous footprint of proline, for example, is essentially what we obtain if we extend the calculation of the indexes to all the possible, the known protein structure, and the same, this represented by this purple kind of pink purple color here, is valid for glycine, for example. No? And now I think that the time is finishing, or maybe it's finished yet. And so let me go to conclusions. And the objective of this talk was to communicate that actually hyperspherical coordinates can be used to build up invariant indexes for systematic classification of large molecular structures. And particularly, we can get interesting indexing to classify shape coordinates and to obtain, in a sense, a kind of footprints or fingerprints of amino acid in proteins. As a further perspective use, we can, I have to say that my idea is to use this index to measure how much chiral it is, a single amino acid, in the large variety of protein structure, how this chirality measure is distributed in the realm of native protein structure. I finish here, and let me say thank you to you all for the attention, and that's it.
Thanks, Andrea, for the nice talk. We have a very short time for one question because we arrive large in the time. Please, the paper is open to discuss. Okay, seems that you have very clear, and I pass the chair position to you again. Okay, see you.
Okay, just a second. Let me cancel the sharing. I don't know if you see me or see the slides.
We see you.
Okay, good. Let me introduce the next speaker of the second part of this session, which is Damiano Ferri, which I see is well connected, and his contribution is about the binary classification of proteins by a machine learning approach. Please, Damiano.
Hello, everyone. This is the paper that I present now. The other contributors are Marco Simonetti, Andrea Lombardi, Noelia Faginas-Lago, and Osvaldo Gervasi. We will now see a brief introduction. Then we will describe the system we have created, and finally, we will make the final consideration. In this work, we present a system based on a deep learning approach by using a convolutional neural network capable of classifying proteins chains of amino acids based on the protein description contained in the protein data bank. Each protein is fully described in its chemical, physical, geometric properties in a file in XML format. The aim of the work is to design a prototypical deep learning machinery for the collection and the management of a huge amount of data, and to validate it through its application to the classification of a sequence of amino acids. Then we apply the described approach to a more general classification problem in biomolecules related to structural properties and similarities. At the start of the work, we was able to choose from the XML and the PDB format when we download the dataset. We choose the XML format because with our programming language was easier to manage and extract the information of the proteins. In the last few years, the recourse to machine learning application has become widespread in molecular dynamics.
Damiano,
yes,
sorry.
Yes.
The quality of the video, it's very low. I don't know why.
Oh, okay. Let me check.
Damiano, I guess it's an issue of resolution of your PC because we see only part of the slides.
Okay.
Not the entire.
let me restart the presentation. Okay. Let me check.
No, it's better.
Okay.
No, it's fine.
Better?
Yes,
Good,
it's
good.
much better. Good. Okay.
Okay. Thank you. In this work, we have posed the basic problem of classifying as real a protein given its amino acid sequence using deep learning. We select as a model the convolutional neural network. We could try the recurrent neural network, but we choose the convolutional neural network because this type of model can be processed with a low-end hardware, and the recurrent neural network needs more computer power to execute the calculation. And the main advantage is the capability of enabling to use the model developed on a plurality of platforms and even on dedicated boards. The system must be able to correctly classify a sequence of amino acids, telling whether it represents a protein, a possible real protein or not. We developed all the system in Python 3 using Google Colab as a platform. And in this slide, we can see the difference from PDP and the XML format. The dataset was very big. In total, we can see over 2 terabytes of data. We extract only the important information from the dataset. We was able to manage 100,000 instances. After that, we apply data augmentation. We read each molecule in both directions. Okay, and we doubled the number of the instances. In the second phase, we generated the fake samples because in the machine learning approach used, we must describe a real and a false proteins in equal number. Okay. Then we labeled the proteins as true protein and false protein. The false protein was all the false proteins are generated by a mutation. Okay, we randomly mutate the real proteins by changing just a short percentage of atoms. Then we build a model. We test several models, and we present in this picture our final model. We can see on the top an embedding layer because the input is composed by a list of atoms. Okay, and each atoms is another list. We can find the first element that is the name of the atoms. And then we have the X, the Y, and the Z, because we map the coordinates of the atoms in the space. Okay, and with the embedding layer, we transform this list with 4 elements to a new element with just 1 value. Then we transport this information to the first convolutional layer, and then again to another one convolutional monodimensional layer. We introduce a max pooling layer to extract the information. Then we introduce another one convolutional and another one max pooling layer. The final layer is just a dense layer that this layer just do the classification. Okay. Analysis of results. The results obtained are very encouraging. We get 95% of accuracy, classifying true and false proteins. And now we can see some graph. The first graph is the model loss. We test the system. We train the system in 50 epoch, and we can see how the train and the test set accuracy change over the epochs. And then the confusion matrix, we can see the true the true predicted, the false positive, and the correctly false proteins classified. This is the confusion matrix normalized, the value in percentage. Despite the very promising result shown by the simulation, we believe that there is considerable room for improvement, both in the selection of the system's hyperparameters and in the preparation and management of the data needed to learn the machine. And then our idea is to continue to explore the possibility of using the convolutional neural network rather than the recurrent neural network, because the convolutional neural networks are lighter and can be run on a low-end hardware. Thank you for your attention.
Thank you, Damiano, and there is room for questions. Is there any question? Okay, if there are no questions, I have curiosity for Damiano. And can you hear me?
Yes, yes.
Okay, so I want to ask
is the low on battery just during the presentation, of course. Okay.
Okay. No, I just want to ask you, how difficult do you think that this approach can be applied to different kind of molecules, just not only proteins, for example, DNA or even more complex structures which are common in biochemistry?
Of course, this is a very interesting question. I think that this is another test case, but will be, of course, very interesting to try just the developed code in Python with another dataset, just to get more data and try to view if our model can be transported and used in another problem.
Okay, thank you. If there are no more questions, we can. I think we can close the workshop, and let me say thank you to you all for participating, and see you in the next days for the prosecution of the ICCSA 2020 conference. So see you. Goodbye.
Thank you. Bye bye.
Thank you.
Thank you,
for
everyone.
the organization.
Thank you. Bye bye.
Thank you.
Bye bye.
Bye.
Bye. Bye bye. Bene, molto bene. Abbiamo finito.
Just wait for the stop of the YouTube live session.